Hello and welcome. In today's lesson, we will discuss simplifying polynomials. Our conversation will be focused on adding and subtracting polynomials and multiplying them. When it comes to multiplication, we'll talk about how we multiply a monomial by a binomial, and then how we multiply two binomials together. This lesson can be used for grade 10 academic or applied, and why not for grade 9s as well. So let's get started. Polynomial expressions are made of one or more terms. They're expressed as the sum or the difference of them. And here is an example. So 5x squared y plus 3x squared plus 2. So this is a polynomial expression, and I am going to add one more term in here. And in this polynomial expression, we have 1, 2, 3, 4 terms that are either added or subtracted to each other. Now, the degree of a term equals the sum of the exponents of all the variables the term has. So we're going to say the sum of the exponents of its variables. As an example, I will take the term 3x squared y4z. In this case, we will say that the power of x is 2, the power of y is 4, and the power of z is 1. So the degree of this term will be 2 plus 4 plus 1. And that would equal 7. So this is a 7th degree term. Now, the degree of a polynomial equals the degree of the highest degree term. What does that mean? If you look at this polynomial expression that we have here, well, the degree of the first term will be 3, and that's because we have a power of 2 plus 1. The degree of the second term is 2. The degree of the third term is 0, and the degree of the last term is 1. The highest degree term is 5x squared y. That makes the polynomial third degree. A constant number is considered to have degree 0. The next concept we want to go over, and the last one, is the like terms. Like terms are terms that have the exact same variables raised to respectively exact same powers or exponents. So let's get started with adding and subtracting polynomials. So there are 3 steps we want to follow here. Identify the like terms in the expression, group the like terms, and then simplify the like terms. Example number 1. We have 5p squared minus 3 plus 2p squared minus 3p cubed. And what we have in here is the addition of 2 binomials. Step number 1, we need to remove the brackets. So 5p squared minus 3 plus 2p squared minus 3p cubed. And once we remove the brackets, we identify the like terms. Remember, like terms must have the same variable raised to the same powers. First term has p squared. Second term doesn't, so they're not like terms. Next term has p squared, so they must be like terms. And minus 3p cubed is not like terms with any term in this expression. So we'll group. That's step 2. And then the next term is negative 3p cubed, and then minus 3. Now we are going to combine like terms. Remember that when we combine like terms, we work with the coefficients only. So positive 5p squared plus 2p squared equals positive 7p squared. And then we have nothing else to simplify, so we leave the rest of the expression as is. Another thing I must mention is that it's better that we write each step completely with all its terms. Write the equal sign aligned here on the left side, and write the expression, the simplified expression, aligned as well. Now there is one last thing I want to mention, which is very important. Whenever we state the final answer, we make sure that the terms are listed from highest to lowest degree. Now, first term here is degree 2, second degree 3, and this one here is degree 0. So the first term is negative 3p cubed. Remember, the negative sign before the term will always go wherever the term goes. Plus 7p squared minus 3. And this will be the correct answers and the final answer. Okay, next question. We have an example of subtracting two polynomials. So first, remove brackets. So that means we have a3 minus 2a squared. Now remember, here you have a negative sign in front of the brackets, which means that the sign of each term inside brackets must switch to opposite. You can think of this as if you're multiplying the brackets by negative 1. Okay? So, here we go again. Negative 3a squared. And negative 4a cubed will change to positive 4a cubed. The next step will be identify the like terms. So the like terms I see here are a3 and 4a3, and negative 2a squared and negative 3a squared. So I will group them. a3 plus 4a3 minus 2a squared minus 3a squared. If you're probably wondering whether you can simplify right away and skip the step that I just wrote, which is grouping like terms, you can do so, but wait until you gain enough confidence in operating with polynomials. So a3 plus 4a3 means that we're adding the numbers 1 and 4 and giving it the variable a3. 1 plus 4 is 5, a3. For the next two terms, we have a similar situation. So we have a squared terms, and we operate only with the coefficients, which means we're taking negative 2a and negative 3a. So negative 2 minus 3 is negative 5, and we're leaving a square in there. A common mistake people make is whenever they add like terms, they change the exponents. To help you not make this mistake, I'll bring you an example. When we are adding 1a cubed to 4a cubed, it means that you have 1a cubed, and I'm going to call a cubed positive, this green a cubed, and you are adding 4a cubed, so you're adding an a cubed and another a cubed and another a cubed and another 1. So in total, we're going to say we have 1, 2, 3, 4, 5 a cubes. And that's why the power of the term and the power of the variable will not change when we add The same thing works with subtraction. Okay? Now, the next question is about multiplying polynomials. So we're going to take a look at the multiplication of a monomial with a binomial. Remember, we call this the expansion method, so our process, and we are expanding by multiplying the monomial 2x by every term inside the binomial. So that means 2x will multiply negative 2x, and then 2x will multiply negative 3. So this is where the 2x is, all right? The one that was inside the outside the brackets. So 2x times negative 2x would equal, remember that we multiply the coefficients together, and I will show the work in here just in this example. So that's same as 2 times negative 2, and then x times x. Okay, so that means we have negative 4. X times x is x squared. In a similar way, we multiply 2x by negative 3. So the numbers will always multiply each other. The variables multiply each other. So that would be negative 6x. And this will be the answer to example I in multiplying polynomials. Okay. Next question is 7 times negative 5e minus 8. Same idea. We're taking 7 and multiplying it by negative 5e, and then negative 8. So 7 times negative 5v plus 7 times negative 8. So that's negative 35v minus 56. Now, in the next examples, we'll focus more on multiplying two polynomials. The game changes a little bit at this point in time. So when we multiply by two binomials, we use a method we call FOIL, if you remember, from grade 9. So what does that mean? FOIL means that you're first multiplying the first terms in each binomial. So the first term in the first binomial is 2n, and the first term in the second binomial is 6n. So you're multiplying the first terms first. So that means we're multiplying 2n by 6n. And the next thing is multiplying the outside terms. So multiplying the outside terms means multiplying 2n and 1. They are on the sides of this multiplication. That's why we call it outside terms. So that's what letter O stands for. So we have plus 2n times 1. And then we multiply the inside terms. The inside terms are 2 and 6n, so the terms that are inside the expression. And we'll write plus 2 times 6n. And last but not least, we will multiply the last terms. The last term means the last term in the first binomial multiplied by the last term in the second binomial. So that means we're multiplying 2 by 1. So that's the last term. Sorry. I didn't want this to happen. Okay, perfect. So that means we're multiplying 2 by 1. I know this seems long now, but it will be a shorter process when you just get used to it and practice it well enough and long enough. So that would be 2 times 6, 12, n times n squared. So we'll say 12n squared plus 2n times 1, 2n, 2 times 6n, 12n, 2 times 1, 2. And now we have to look for like terms. I see that here we have two like terms. The terms 2n, and 12n. Let's make this perfect. So here we go. We have 12n squared first, plus 14n plus 2. Okay. You can continue the next example on your own. I'll move on to the third example, 2a minus 1, 8a minus 5. So again we go. 2a times 8a, first terms, right? That's 16a squared. 2a times negative 5, negative 10a. The inside, negative 1 times 8a, minus 8a. And then last, negative 1 times negative 5, positive 5. And now you look for like terms. The only like terms we see here are negative 8a and negative 10a. So 16a squared is by itself. Negative 10 minus 8 is minus 18a, and then plus 5. The last example in multiplication is 4p minus 1 squared. So you can look at it as 4p minus 1 multiplying itself, because that's what squaring a number means. So again we go FOIL. 4p times 4p, 16p squared. 4p times negative 1 minus 4p. Negative 1 times 4p minus 4p. Negative 1 times negative 1 plus 1. So simplify by grouping like terms. They're already grouped, and simplifying them. We get 6p squared minus 8p plus 1. Okay. Now, we are going to take a look at squaring binomials. Squaring binomials is a form of binomial multiplication, but we want to look for some patterns in here. So we are going to square the sum of two terms, which means we're multiplying x plus 3 by x plus 3, which is x plus 3 squared. So again we go x times x, x squared, x times 3, 3x, 3 times x, 3x, 3 plus 3, 3 times 3, sorry, that's 9. So x squared plus 6x plus 9 is the answer. Next, 2x plus 5 times 2x plus 5. Again, we have 2x times 2x, 4x squared, 2x times 5, 10x, 5 times 2x, 10x, 5 times 5, 25. So that's 4x squared plus 20x plus 25. X plus 7 squared, so that's x plus 7 times x plus 7. So we have again x times x, x squared, x times 7, 7x, 7 times x, another 7x, 7 times 7, 49. So the answer is, just trying to make this better and fix my mistakes, 14x plus 49. Okay, so in the next list of examples here, we have multiplication of two binomials, but unlike in the previous examples when we had a plus in between the terms in each binomial, now we have a minus. So let's see what we get here. X times x, x squared. X times negative 3, negative 3x. Negative 3 times x, oh, another negative 3x. Negative 3 times 3 is 9. So that would be x squared minus 6x plus 9. Okay, next question. 2x times 2x, 4x squared. 2x times negative 5 minus 10x. Negative 5 times 2x minus 10x. Negative 5 times negative 5, positive 25. So we have 4x squared minus 20x plus 25. Last question, x minus 7 squared. So we had x plus 7 squared before. So x minus 7, x minus 7. So x squared. Now minus 7x. Minus 7x again. And then plus 49. Simplified form is x squared minus 14x plus 49. And there we go. We are done. And we want to answer some questions here. How many terms did we obtain when we multiplied two binomials in the above examples? So when we had the square of a binomial, which is multiplication of two binomials, we got 1, 2, 3 terms. Great. And then 3 terms. So in all the multiplications above, we got 3 terms. So we're going to write in here that we got 3 terms. Now, how were the expressions in the first column compared to the expressions in the second column? Were they same or were they different? So what did they have the same? Well, they had the same one thing. If you look at them, x squared plus 6x plus 9, and compare it with x squared minus 6x plus 9, I'm going to say that we see the exact same terms or exact same expressions except for one. So we're going to write, we see same terms for the first at least, but the only difference is the middle term had or is negative, I should say. In the second multiplication, right? Now, let's check and see if that is true for the rest of the expansion. So here is the plus, and here is with the minus. Again, you see the exact same terms, only the middle term is negative. Let's check the last one. So again, we have this one here, and this one here. Oopsie. Okay then. So exact same terms, just the middle term is negative. So what we're going to do now is expand a plus b and a minus b. So here we go. A plus b squared equals a plus b, a plus b. So if you expand here, you get a squared plus ab plus ba plus b squared. So that's a squared plus 2ab plus b squared. So you get 3 terms. If you expand a minus b squared, you have a minus b times a minus b. So that's a squared minus ab minus ba plus b squared. So that's a squared minus 2ab plus b squared. So we are going to use the pattern in order to expand the following. I'm going to rewrite here though what we just discovered, because what we just discovered was a very important formula that we're going to use in the future lessons and in grade 11 and in grade 12 as well. So we say that a plus b squared is a squared plus 2ab plus b squared. And a minus b squared is a squared minus 2ab plus b squared. So it's the same idea. In other words, we're going to say that when we expand a binomial to the power of 2, then the expansion will give the first term squared. So first term squared, and then the last term squared. And there is this middle term in here, 2ab. And we're going to say that the middle term is twice the product of first with the last, because we're multiplying by 2 the product of a and b, where a and b are first and second term. So twice the product of first with last. And the same idea applies to, or same explanation I should say, is for the a minus b squared, with the only difference that we have a minus here. So now that we know this, we're going to expand binomials to the power of 2 faster. So we're going to say x plus 4 squared is the first term squared plus twice the product of the first with the second plus the last term squared. So that's x squared plus 8x plus 16. Next question. We have the first term squared minus twice the product of the first with the second plus last term squared. So that's k squared minus 10k plus 25. So we don't need to use foiling when we are expanding a binomial to the power of 2. Okay? Same idea applies to the next question. So we have the first term squared minus twice the product of the first with the second, and then plus 1 squared here, the last term. So that's 4x squared minus 4x plus 1. Now you're probably wondering, why do I have to do this? Foiling just gave me 2 steps, and here we still have 2 steps. Well, the reason why we want to do this is because these kind of exercises will lead us to better understand how to go from the expanded form to the factored form, which will be our next lesson. So last example, we have 3y plus 7x squared. That's 3y squared plus twice 3y 7x, and then plus 7x squared. So that's 9y squared minus 42xy plus 49x squared. Okay? Now, this is what we call actually a special product. And I'm going to write this down here with using one of my favorite colors. So, special products. Okay, so we have just learned the first special product, which is a plus or minus b squared equals a squared plus or minus 2ab plus b squared. Now, the next special product that we are going to look at is what we call the difference of squares. Okay, let me do this. I don't like that. Let me make it a little better. Okay, I probably should give up, but I won't. Alrighty, I like this better. So the next special product is what we call the difference of squares. Let's see what happens there. Now, when we have difference of squares, or we get difference of squares when we multiply a binomial such as x plus 4, with the binomial x minus 4. So you see the difference here is that here you have plus 4, here you have minus 4. Everything else is the same, okay? So here we go. X times x, x squared. X times negative 4 minus 4x. 4 times x plus 4x. 4 times negative 4, negative 16. So x squared, these two terms will simplify, and then minus 16. Oops. From the multiplication of these two binomials, I only got two terms. What did just happen here? Maybe it's a coincidence. Who knows? Let's move on to the next example. So in the next example, we have k times k, k squared, k times 5, 5k, negative 5 times k minus 5k, negative 5 times 5, negative 25. Let's check and see if you can simplify. So we have k squared going with nothing else. 5k minus 5k is nothing. Then minus 25. Two terms again. Great. Next example. Again we have 2x times 2x. 2x times 1. Negative 1 times 2x. Negative 1 times 1. So 4x squared minus 1. Next example. 3y plus 7x, 3y minus 7x. So 3y times 3y. 9y squared. 3y times negative 7x, negative 21xy. 7x times 3y, positive 21xy. And the last terms, negative 49x squared. So these two terms will simplify, and the answer would be 9y squared minus 49x squared. So as you see here, in all these multiplications, we obtained a binomial most simplified form. So, and we didn't take just one example. We had quite a few of them. We looked at quite a few of them. So what just happened in here? So we're going to say that we obtained two terms. And what happened was that these middle terms simplified. Okay? If we can call it the middle term, because that's where the terms came from, right? So the middle terms simplified. So what we're going to do now, in order to make this into a rule or a theory, we are going to expand a plus b, a minus b. So again, we're going to go a times a times negative b. So that's a squared minus ab. And then b times a. So as you see here, because the signs are opposite, that's why the terms simplify, right? And then minus b squared for the last term. So we're going to say that a plus b times a minus b equals a squared minus b squared. We call this the difference of squares, because if you think about it, we're finding the difference, or we're getting the difference of two squared terms, right? So here we go again. This is going to be our next and the last special polynomial that we're looking at today. We're going to use the pattern now to expand the following expressions. So x plus 5, x minus 5. Well, we're going to say they are exact same except for the sign in the middle. So that means we're getting difference of squares. So x squared minus 25. K minus 3, k plus 3, k squared minus 9. 7x minus 2, 7x plus 2. So it would be 7x squared minus 2 squared. So that makes 49x squared minus 4. And last, 3y plus 4x, and this must be y, by the way, sorry about that. 3y minus 4x, and we're going to say that we have 3y squared minus 4x squared. So that's 9y squared minus 16x squared. Okay? So this is the end of the lesson, and I know that it was probably quite a lot to think about, but it's very important so that we start the unit of quadratic equations strong and we build some good foundations of polynomial multiplication, simplification. So what we learned today, again to recap, is adding and subtracting polynomials, okay, multiplying polynomials, monomial, binomial, and binomial. We went over FOIL, and we learned how to square a binomial, which gave us 3 terms, and a perfect square trinomial, we call it, and a special product such as these two. So we kind of summarize them. Now I want to add one last thing in here. We have a very special name for a squared plus 2ab plus b squared for this trinomial, and I'll point at it right now. So the special name we have for it is a perfect square trinomial. So this is called a perfect square trinomial. Why is that? Any polynomial or any number that comes from something else squared is called a perfect square trinomial. Like number 2 squared equals 4, so 4 is a perfect square. A squared plus 2ab plus b squared comes from a plus b squared, so it's a perfect square trinomial. So don't be confused if you ever hear the term perfect square trinomial, because that's the meaning of it, okay? And there are 2 types of special product: the perfect square trinomials and the differences of squares. That's all you're learning in grade 10. Okay, so I know the lesson was too long. I hope it made sense,